Okay, today's topic is going to be 9.3, which is interference patterns and single slits and double slits and multiple slits. So it's just going to be an addition to what we learned earlier with double slit interference and interference patterns. So if you look at the essential idea, interference patterns from multiple slits and thin films produce accurately repeatable patterns. That's kind of the big picture. We talk about patterns of iridescence in animals, and notice that this little serendipity part here, the first laboratory production of thin films was accidental. This is something they mentioned in your textbook quite a bit, so you probably want to know about it. And it turns out that the discovery of this thin film interference was an accident in a laboratory, and then lots of uses have come from that. So we'll talk about Young's double slit experiment some more. We'll look at modulation of interference patterns, multiple slit interference, and thin film interference. Some pretty cool stuff. Notice that the equations aren't too bad here and look pretty similar to things that we have seen before. So the first thing that we will do is go back to Young's double slit experiment. Remember, Thomas Young proved that light was a wave and had wave properties by shining coherent light through two small openings and getting a interference pattern on a screen because of the light diffracting through those small openings, interfering with itself, creating these bright and dark fringes. One of the things that you'll want to remember is what the word coherent means. This only really works well if the light is of the same wavelength and if the sources from the two slits or the two openings have a constant phase difference. Ideally, they'd be in phase with one another, but even if they're out of phase, as long as that phase difference stays constant, then everything should work out fine. And remember that the fringe pattern that occurs with two small openings with a double slit, you'll get equally spaced fringes that in an ideal world will be equally bright. So the bright and dark spots will be equally spaced. Notice that's different than when we did single slit interference, where the central fringe, the central bright spot was the brightest, and then as you moved away from that central bright spot, their intensities diminished. With double slit interference, that shouldn't occur in an ideal world, where the two slits are incredibly small. How was Young able to do this in the early 1900s? Well, he basically he used a candle as his light source, and he passed the light of that candle through a single slit where it would diffract, and then it would hit the screen that had the two slits before going to the final screen. This helped ensure that the light going through the double slits was coherent, that it was in phase, or at least had constant phase shift as it was doing that. Nowadays, when we do this kind of an experiment, we use laser light, which is just by definition, the way it's created, it is coherent light. And remember that the way this whole interference pattern works with double slit interference, it has to do with path difference, that the fact that the light from one of the openings has traveled a different distance than the light from the other opening when it reaches the screen, except for in that very central spot, of course. And if that path difference from the two openings is some whole integral number times the wavelength, you'll end up with constructive interference. And if that path difference is some half of a wavelength, either 1/2 or 1.5, 1/2, 3/2, 5/2, so on, you'll get destructive interference where the light meets. And so as the angle changes, that's what creates that interference pattern, is the path difference from the two sources to the screen. Hopefully that's a review for you. This is stuff that we've talked about a number of times. You might remember that back in topic 4, we used an equation S equals lambda d over d. This equation will still be valid in this unit, but we're just going to elaborate on it a little bit more. And the equation that's in the data booklet for topic 9.3 looks like this. Very similar equation. This is just allowing us, this is actually taking the sine of the angle into account and allowing us to account for different fringes. So imagine that this is your central bright spot. This is your first fringe, which means the path difference here is actually one complete wavelength. We'll just call that lambda, right? If you look at this triangle and the angle, this angle theta that's created between the central bright spot and the first maximum after that, the first fringe after that, is going to be equal to this angle. So that angle right there is also theta. We can do some basic trigonometry and say that the sine of this angle theta will equal, let's see, opposite over hypotenuse. So sine of theta equals the opposite side, which is the wavelength, over the hypotenuse, which is the distance between the slits. And with a little rearranging, we end up with this equation here. And then we just add the integer n, 1, 2, 3, 4, 5, depending on which fringe we're talking about, whether it be the first one, the second one, the third one, the fourth one. So that is the equation in topic 9.3 for double slit interference, relatively straightforward. So with that, here is an IB question, 4-point question that you would see on paper 2, potentially, having to do with interference. Why don't you go ahead and hit pause, look at it, and work on it for a little bit, and then we'll go through it. Okay, getting ready to go through the answers, so hit pause if you are planning on working on these and have not yet done so. So for A, 2 points, basically asking to explain why there's an interference pattern, everything we've talked about. You need to, let's see, if you mention something about there being diffraction at the slits, or the slits are coherent sources of light, that's worth a point. If you said something about the path difference or the phase difference when that light reaches the screen, that's another point. And if you talked about constructive and destructive interference, that's another possible point for 2 maximum. If you just said interference and you didn't mention constructive or destructive, that's not going to help you at all because they mentioned interference in the question. Okay, let's go with question 1B. 2 slits are separated by 2.2 millimeters. Let's see, we're looking for the distance from M to P. Great. Since when we're looking at this problem, they didn't give us anything to do with an angle. They gave us the slit separation, the distance to the screen, and the wavelength of light. I'm actually going to go with our original equation. I could solve for the angle, but I'm going to just go with our original equation first. So this will be the first thing that you'll do is you can use the original equation to find out the distance between each fringe pattern if you want. You could throw the, well, I'll talk about this next part later. So let's solve for the S, the separation between fringe patterns. So just plugging in numbers for the variables, you got wavelength, you got the distance to the screen, the distance between the slits, you will get a distance of 5.3 times 10 to the negative 4th meters for S. That's how far apart each fringe is. Then, noticing that the distance between M and P is 1, 2, 3 fringes apart, just multiply that by 3 for your final answer of 1.6 times 10 to the negative 3rd meters. There you go. So when we talk about double slit interference, we often talk about the fringes being equally bright or having equal intensity and having an equal spacing. That is true in an ideal world where the slits are infinitely smaller, point sources. In the real world, the slits will have some kind of an opening. They'll have some width to them. So it turns out the wider they are, you start to get single slit interference interacting with this idea of a double slit interference pattern. So when you have in the real world where the slits actually are getting relatively large relative to the wavelength, let's say a couple times the wavelength, you get what's called a modulated pattern. So notice with this diagram, the blue dotted line is the pattern you would expect from a single slit interference pattern with a bright central maximum and then a dark spot and then diminishing fringe patterns getting less and less intense as you move away from that center. Since we have 2 slits instead of 1, what you end up with then with this red line is you get these fringe patterns, right? Bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, embedded within the single slit pattern. So this is what's created by the double slit opening, and the intensity of the double slit pattern will diminish like a single slit pattern. So that's one of the things that happens when the width of a double slit interference pattern actually, the slits increases. You basically end up with a single slit pattern with the double slit interference pattern embedded within it. So since we just talked about that, we can look at this IB multiple choice question about that. Why don't you hit pause and try it? It should be super easy because we just talked about it. Go ahead, hit pause. It's okay, you can do it. And since this is what we just talked about, hopefully you're recognizing that D is the correct answer. Notice that you have a combination of the single slit and the double slit interference pattern in one, since we're talking about slits that have finite width. They actually have width. That's what this question is getting at. Now the interference pattern that gets created when we have more than 2 slits, where we increase the number of slits, also gets a little bit crazier. So notice this little picture here. Here's the interference pattern with 2 slits. Just do a little the little bright spots. 3 slits, notice you still have 2 bright spots, but you have a less bright spot in between them. With 4 slits, still have 2 bright spots. And notice that they're staying the same spacing apart, but now you have 2 fainter spots in between them. And with 5 slits, you get 3 in between them, and so on and so on and so on. So as you increase the number of slits that you're passing light through, the primary maxima, here's the primary maxima to start with, notice that they get thinner, right? They get thinner as we increase the number of slits, and the intensity also increases. And their separation never changes, all right? The same pattern's happening. The separation doesn't change because we're not changing how far apart the slits are and things like that. Something to recognize is that the number of little minima, the number of secondary maxima that occur in between the bright spots is actually n minus 2. So with 3 slits, we had 1. With 4 slits, we'll get 2. With 5, we get 3, and so on. And the more slits we get, this picture doesn't show it very well, these intermediate maxima actually will get dimmer and dimmer and dimmer. So the more slits you have, they will start to fade away, and all you will start to see are these very pronounced bright spots. And the intensity of the central maximum is proportional to n squared, proportional to the number squared. So let's say we start off with an intensity here. Well, 3 slits, we get 9 times that. 4 slits, we're going to get 16 times that, which 16/4 is just 4. And 5 slits, we're going to get 25 times that because it's proportional to the number of slits squared. In this unit, you should also be familiar with what's called a diffraction grating. And we played with diffraction gratings in class. We actually did a lab where you predicted where the bright spot would occur when laser light passed through a diffraction grating. Also, when you use these little party glasses that created the rainbows, so when you look at light, those are diffraction gratings as well. And basically, it's a piece of material that has a lot of slits very close together that will cause light and cause a diffraction pattern. What I was just talking about previously is, in this case, here is one of our maxima, here's another maxima, and notice you don't even see the little the little brightness spots in between these 2 maxima because they become so discrete and so fine because there's so many lines. So what a diffraction grating is, it's basically a device with a huge number of parallel slits that have very negligible width. You know, typical is like 600 lines per millimeter, so they're very, very fine, very, very thin little openings for the light to pass through. When light passes through a diffraction grating, you get this interference pattern with very distinct, very bright maxima, and those intermediary ones, the minima that are in between those maxima, are basically negligible. They basically go away. One of the things that diffraction gratings are used for is to very precisely measure wavelengths of light. They're called spectrometers, and most spacecraft that we send to investigate other planets and other places will have spectrometers in them to help us very carefully measure the light from the atmosphere, from the surface of the planet, which can teach you all sorts of things about those objects. We also use diffraction gratings, again, to see cool rainbows when you're wearing those party glasses, that when you look at light, you see the rainbows everywhere. And just be aware that IB has mentioned spectrometers a couple times in this unit, so it's just a device that you probably want to have some awareness about. If you want to get more information on them, check it out. You can do some research and see what you can find out. Now, the last subject in this topic 9.3 is thin film interference, where we're not passing light through slits at all, but it's happening because of reflection on thin films, and it's a fascinating topic. You'll see it most frequently on the surfaces with oil sitting on water or soap and bubbles. Notice in both these images the cool rainbows that appear on the bubble and also on the oil slick that's on water. And the reason you get these cool different colors and rainbows is because of this process called thin film interference. And again, this is something that was discovered in a laboratory by accident. It was something that had been observed before, but then the discovery of why it was happening was purely accidental. It's a really neat phenomenon when you see it, and it has everything to do with reflection and interference. So let's see if we can break this down conceptually a little bit before we get into the mathematics of it. But imagine that you have light coming onto a surface right there, right? And when it hits the first boundary, some of the light's going to be reflected. This is back to our introduction of waves. And some of the light will be transmitted, okay? That's what happens when waves meet a boundary. That light is transmitted, will hit the back boundary. Let's see, in this case, we've got a film with air. It could be oil and water as well. And when it hits this back boundary, Some of the light will be reflected, and some of the light will be transmitted. What I'm really interested in are these two pieces of light that were reflected off of the top surface and off of the bottom surface, because when the second one comes back out, it will basically rejoin this one, and you will have interference. Depending on how far the light traveled going down and coming back will determine the kind of interference you have. Now, intuitively, you might think, let's think about this. If it goes down and back, and that's a whole wavelength down and back, then when it meets up with the original piece that was reflected, then you're going to be in phase and get constructive interference. And if the path that it takes going down and back is a half of a wavelength, the secondary beam, when it meets up with the first one, since it traveled a path difference of a half of a wavelength, that you would expect it to meet up and interfere destructively. And all that's thinking is really, really good and really, really logical. The only twist we're going to have to add is what happens when this original beam reflects off the boundary. Remember when we talked about waves back when we were doing with slinkies? Sometimes when waves reflect, they invert, and sometimes they don't invert, and that's going to affect what happens here. But conceptually, it all has to do with path difference of the two beams of light. And my drawing is getting really messy here, so I'm going to fix it a little bit by basically erasing it. But just again, the concept I want you to remember is that when light reflects off of the front surface, and then it travels, some of it travels a greater distance and then comes back to rejoin, those two pieces of light will have different path differences, which will cause different interference patterns. That's the basic concept behind thin film interference. It's a pretty cool one, and we'll dig into it a little bit more deeply here. So the thickness of the film will determine what the path difference is, okay? Whether you get constructive or destructive interference. And so if you have oil on water, for example, the thickness of the oil changes all the time. It's not uniformly thick. And so you're going to get different wavelengths, different path differences because of the different thicknesses, which will constructively and destructively interfere different wavelengths, making some colors of light be brighter and some be diminished, and that's what creates the rainbow that you see. The same thing happens on the soap film. The thickness of the soap is changing, and so the path difference is changing, and that's what causes the different colors of light, the different wavelengths to be interfered either constructively or destructively, and the end result is that you see a rainbow. Now, the little twist we have to throw at you is that when light hits, or any wave hits a boundary, if the material it's going into has a greater index of refraction than what it's coming from, so in this case the film has a greater index of refraction than air, and you can tell that's happening because remember with our unit on refraction, when the light ray bends towards the normal, the incident ray, or what the refracted ray bends towards the normal, you know that this material has a larger index of refraction. If that's true, if the material has a larger index of refraction, then the reflected ray will invert. We'll have a 180-degree phase change, okay? So by that same reasoning, the reflected ray back here, which is going into a less dense medium, the one that reflects off that boundary, does not change phase. Because of that, our path difference has to be opposite of what we think. So if the trip down and back is now a half wavelength, down and back is a half wavelength, which means the film is a fourth of a wavelength thick. Since this first reflected ray inverted, then if this is a half of a wavelength path difference, then you will end up getting constructive interference where before we would have gotten destructive. And that's all because of the phase change. So really, it's just the opposite of what we used to talk about in this situation when that first wave inverts. And in IB, instead of saying invert, sometimes they'll say it undergoes a phase change of pi radians, okay? The other thing I want you to recognize about this diagram that's a little bit deceiving is we always draw these things at an angle so that you can see them better. In reality, oftentimes we're talking about pretty much straight down and straight back, but it just gets hard to draw that. So notice that if the light's going straight in, some of it's going to reflect back, some of it's going to go in and then reflect back, and there you have your two path differences, and you get your interference pattern. So here now are the equations. These are in your data booklet. These are the equations associated with thin film interference. And notice that you get constructive interference when the path difference has a half of a wavelength integer. M here is just an integer, 1, 2, 3, 0, 1, 2, 3, 4, 5. So Remember before we were talking about a path difference, so a half wavelength will usually give destructive interference. In this case, it gives constructive because of that phase change off of the first interface we're assuming is true, okay? If for some reason we're dealing with thin film interference where light is going into a medium where the index of refraction is less, then these equations are just opposite. But I can't imagine that really happening very much. So what are some of the assumptions we have with these equations and some of the things you need to know? The first assumption is that, yes, that there is a phase change at the first surface of pi radians. Again, that only happens when light is reflecting off of a medium that has a greater index of refraction. And these equations will switch if, for some reason, there is no phase change off of that first surface. In this equation, D is the thickness of the film, okay, how thick it is. N is the refractive index of the film that is creating this interference pattern. And finally, lambda is the wavelength of light in air. Now, the reason we get the lambda and this N in here and the 2, again, the 2 has to do with the fact that the light had to travel in and back out, right, of the thin film. And the N and the lambda account for the fact, this is kind of funky, but it accounts for the fact that also the wavelength of light changes in that film. So we're not going to mess with it too much. Instead, we're going to, with these equations, we're going to use the index of refraction of the film and the wavelength of the light in air, and that will work itself out for us. You can see the more details about that in the textbook if you'd like. Now, aside from creating really cool rainbow patterns on oily surfaces and on bubbles, what good is thin film interference? Well, there are some uses for it, and one of the probably coolest uses is in stealth aircraft, like the stealth bombers and things like that. And what the military has learned to do is that, you know, you got your airplane. Let me draw a little airplane. Let's say you got your military aircraft that you're trying to fly all stealthily and you don't want to be detected. Well, the way people detect aircraft generally is with radar. In radar, you basically have some sort of radar transmitter that sends out waves, right? They bounce off of things, and when they bounce off of things and come back, you can measure how long it takes them to come back and figure out where those things are. That's what radar does. Stealth bombers use a variety of technologies to try to be invisible to radar, and one of the things they do is they coat their surfaces with special materials. Let's say this is the wing. The wings and the whole body of the aircraft gets coated with a thin film. And the thin film is exactly as thick as it needs to be so that when the radar waves hit it, they go through, they bounce off, they will destructively interfere with themselves and essentially disappear. And so the aircraft becomes invisible to radar waves, which is pretty cool if you think about it. All right, here's another IB question, actually 3 questions for you to practice. Relatively straightforward stuff. Go ahead and hit pause and give it a try. Okay, I'm going to go ahead and give you the answers here. I'm not going to walk through how you solve them. You should be able to do them with the equations we just had and, you know, ask questions if you can't figure it out. But the answer for A is going to be 440 nanometers. 440 times 10 to the negative 9th meters. For B, you're going to get 110 nanometers. And for C, the reason being is that there would be a full wavelength within the film when this happens. And since there's a phase change at the surface, it means that you will always be getting destructive interference, right? So for constructive interference, the film would need to be 1/4 of a wavelength thick, right? So that the path difference is 1/2 of a wavelength. And then if you double that thickness, the thickness becomes 1/2 of a wavelength, which means the path difference is a full wavelength, which creates destructive interference since there is a phase change on that upper surface. All right, let's quickly review the syllabus and see how we did. We talked more about Young's double-slit experiment. We talked about how the pattern gets modulated using that 1-slit diffraction and the 2-slit diffraction or interference embedded with it, multiple slit interference and diffraction gratings, and thin film interference. Okay? Look through everything that you should be able to do and know. That's a good thing to review. And it's always a good idea to look at the guidance on the syllabus. So you should understand interference pattern from a variety of sources, a variety of coherent sources, such as electromagnetic waves, sound, and demonstrations, okay? So understand that this all can happen with different kinds of waves. Diffraction gratings will only be when things are normally incident. The treatment of thin film interference is confined to parallel-sided films. That's kind of nice, rather than like wavy films. That'd be kind of crazy. Or one that's sloping. Great. And recognize that, and finally, it is good to recognize that the equations listed below are specific to when waves have a phase change at the first interface, and they're not always true. So it's a good thing to recognize that. All right, hope you enjoyed it. Let me know if you have any questions.